So it's finally time in part 4. Sorry, my dog is itching. To start talking math. So we've been talking about solutions. Now I know we've been talking about reactions, but the focus on this chapter is with the aqueous portion, which we haven't talked that much about yet, other than soluble ionic compounds are aqueous. That means they dissolve in water, and insoluble ionic compounds are solids because they don't dissolve in water well. So when we're looking at solutions where we take a solute like sodium chloride and mix it with a solvent like water, and so if that's the case, that means we have more water than we do sodium chloride. Solute, there's the least amount of. Solvent, there's the most amount of. If there are three things in the mixture, there's only one solvent. There can be more than one solute. Okay, with our solutions, and they're always homogeneous mixtures, which means it's evenly distributed, evenly mixed throughout the whole thing. When we do that, I can take salt and water and put them together and make a mixture, and they're not all exactly the same. I can vary the amount of salt and the amount of water that I add. We need some way to identify these solutions with that amount, with that how much salt to water ratio. There are a whole lot of different concentration units, so different ways we can put a number on that, and units we can use just like there are lots of different units of measurement, right? But we're going to focus on one in chapter 4. For those of you that go on to general chemistry 2, you're going to focus on a lot more. You're going to learn a lot more concentration units. But we are going to choose one concentration unit to give us an idea of how either concentrated or dilute a solution is. Something is dilute, that means it's weak. That means you do not have very much solute. If something is concentrated, that means it is strong. It has a lot of solute, or has more solute anyway. You can think of just your daily life with stuff with this. So, like I buy a cleaner, like my spray cleaner that I use to clean my counters and like my antibacterial stuff, um, in a big jug so I can refill my little sprayer. And it's in concentrate, and it says that on there. So that means I have to take, I don't know what it is, a couple of ounces and mix it with like a gallon of water or whatever it is and shake it up, and then I pour that into my spray bottle. So the stuff in the bottle that I buy is way stronger than it needs to be for me to do my cleaning, or than I want it to be, so it doesn't damage like the wood or something. And so I have to add water to it to dilute it down. Okay, so those are terms that we can use in everyday life and in chemistry. Another term with concentrate, so you can buy juice concentrate, which are like those frozen little tubes of juice that when you want to make juice from those, you put them in your pitcher and then you add water and you stir them. So they're concentrated, they're very strong. We add water to dilute them to make them the appropriate concentration to not taste disgusting. And that's the technical term of all of this. But okay, so we're going to start looking at the numbers part of concentration. Of course, being weird. There we go. So again, the concentration is just looking at the amount of solute there is in the solution. Okay. The more solute, the more concentrated it is, the higher the number is going to be. The more dilute it is, the lower the number. So our unit that we're going to focus on is molarity. It's the most common unit we use as chemists. There are many, many other units. There are percentage units, there are molality, there's mole ratios, there's all kinds of things, but molarity is the most common one used in the lab. And the definition of molarity, well, molarity is abbreviated by the capital letter M, and it does have to be capital letter M. Lowercase m stands for something else, and MOL stands for something else entirely. So MOL is moles, capital M is molarity, and lowercase m is a third thing that we have not yet talked about. So with our units, be careful. So molarity, capital M, is moles of solute. So you have to take the amount of solute, convert it to moles, and it's in the numerator, divided by the volume of the solution in liters. So one thing I want to remind you, solute, there's a small amount of it. Okay. Solvent, it's the one there's the most of in the mixture. Solution, that's the total. So the denominator, the volume of solution in liters, means it's the volume after you've mixed all the pieces together. What's the volume of the total? Now, most people memorize molarity by saying moles divided by liters. It's really not quite good enough. You need to be very specific. Moles of solute divided by liters of solution, especially when we get to other concentration units, which unfortunately, for me anyway. I don't know about you guys, but isn't until general chemistry too. Um, the words as well as the units are important. Okay, so you can treat this kind of like we do density, where it's a definition. Density is the mass divided by the volume, right? And so you could treat it like an equation and plug them in. But I'm more likely to treat it kind of like a unit factor, because molarity, well, it can compare moles to liters because it's like miles per hour, right? It's something per something. So we're going to start, before we do the math, is we're going to start talking about how you would go about making a solution where we can accurately calculate its molarity. Okay, so in this picture, this is a volumetric flask. They're wonderful. Their purpose in life is to be the container in which you make a solution, so the container in which you make a mixture. And each volumetric flask has a number on the front of it that tells you what its volume is, how much liquid it holds. I think that one says 250. It might say 150. It's kind of hard for me to read. This was not a picture that I took. Now, on the volumetric flask, there will be a line somewhere. In this case, it's right there. It's hard to see. Okay. But there's one line across that flask. And so what that means is that let's say the front says 250 milliliters. That means that when you take this container and you fill it up from the bottom up until that line, that holds 250 milliliters. So you can mix all your pieces together. Like maybe you're making a mixture of 3 things. That's fine. Mix them together and then fill everything up until that line, and you know that your volume of the total mixture is 250. That is helpful because in our molarity equation, don't we need to know the volume of the total? So one way to know the volume of the total is to make the solution in a container that holds a specific volume and make sure it goes to the line. Okay, so in this scenario, this blue stuff is going to be our solute. And based on the picture, I'm assuming it is copper 2 nitrate because it's blue. Okay, so they're measuring out how many grams of it. We can't see it on the balance, but that number would be right here. Okay, so that would be the solute. Well, back in our molarity slide, moles of solute goes on the top. Now, the balance wouldn't tell you the moles of solute. The balance would tell you the grams of solute. Have we ever thought of a way to go from grams to moles? I don't know. We spent like most of chapter 3 doing that. So our lovely unit factor of 1 mole is equal to the molar mass in grams. Yeah, that's still in play. We're going to be using that a lot this chapter. So we could take the number from the balance in grams and convert it to moles. And then we can, let's say I'm making my mixture with the copper 2 nitrate and water. So I would take the solid that I measured out on the balance and I would carefully pour it into the flask. Okay, and then I would add water, if that's the thing that I'm making the mixture with, to this, and I would have to kind of swirl it as I do this to make sure the solid dissolves, and I would keep adding the water until it got to that line. Now, I would never actually know exactly how much water I added. Water would be the solvent here, but I don't care because I don't need anything about the solvent. I need to know the volume of the solution, which is the total, which is why I would just mix them together until it got to the line. So then I would be able to do my calculations and solve for the molarity. Okay. We'd then have to put a lid on this and then mix it really good to make sure it was evenly mixed. So let's do an example. This time I didn't do copper 2 nitrate. The pretend solution that I'm making is glucose and water. So I'm making sugar water. Okay, so we're supposed to calculate the molarity of a solution made by dissolving 5.00 grams of glucose in sufficient water to form 100 then decimal milliliters of solution. So I'm going to do this calculation 2 ways. One way is to follow the definition of molarity like it's an equation, like molarity equals moles of solute, which I'm going to be specific here and say C6H12O6 divided by liters of solution. And so my goal is going to be to solve for the moles, put it on top, solve for the liters, put it on the bottom, and then divide them. I like to do things all in one step if at all possible. So the other way I'm going to do this is to set it up looking a lot like our dimensional analysis or our stoichiometry problems, where I just cancel out the units to get till the end. Both of the ways that I'm going to do this problem are correct. Both ways would get you the right answer as long as you do everything, correctly. And I'll make sure my favorite one is the one that's all in one step. So the first few examples, I'll do it both ways. And then after that, I'm just going to start doing it the way that I prefer. But if you like it the other way, that's fine. It's just we're going to get to a point in our next video where we need to make sure we can use molarity as a unit factor. So anyway, let's get started. So I'm going to do it using the equation first. So I'm solving for molarity. I need to get moles of glucose, and I need to get liters. So I'm going to start with the moles. We were given 2 numbers, grams and milliliters. The grams is going to help me get my moles. So I'm going to take 5.00 grams, C6H12O6, And I'm going to use the given molar mass, 180.15588 grams cancel, okay, to get myself the number of moles. Now, if this were my final answer, my answer would have 3 significant figures because of the 5.00. I don't want to round yet, though, because this is not my final answer. I need a molarity. This is a moles. So when I do this, I'm going to write 0, so my calculator gives me 0.0277. That would be 3 sig figs, but I'm not going to round yet, so I'm going to write 53743 moles. So what I did to help myself keep track of sig figs, do you see how the 0.0277 are big numbers and I made the 53743 like subscripts? That's my way of remembering the 2 and the 7 and the 7, which I know that last 7 would have rounded up to an 8, but we're not rounding because we're not stopping the number yet. Those are the significant figures. So that number has 3 significant figures. And then what I would need to do here is that takes care of my moles. I need to get liters. Well, we were not given liters. 100 decimal milliliters was 1,000 milliliters in 1 liter. Now, when you do this in your calculator says 0.1. But we got to think about significant figures here. The 100 decimal has 3 sig figs, so I have to add 2 more decimal places there. So now I'm going to plug it into my molarity equation. So I'm going to take the moles and take the liters and grab my calculator. And then now I'm going to look at significant figures. This top number has 3 sig figs. The bottom number has 3. That was an S. 3 sig figs. So my answer should have 3 significant figures. So when I do this math and I divide it, I get 0.2775374. So I'm going to round it to 3 sig figs. So 0.278 would be my molarity of C6H12O6. So that way works perfectly. Okay, that would be my answer right there. Okay, but now I'm going to redo the problem. But this time I'm going to do it the way that I prefer. Now, I didn't plan well for this, so I'm going to have to delete all my work. Just like if it was a real whiteboard. Only this seems to take longer. Sorry. I should have been more prepared. I thought I could fit this all in that space. Silly me. I want to leave the top thing there so we can remember what the definition of molarity is. So this time, I'm going to look at this problem. I know I'm supposed to solve for molarity because it says so. But instead of thinking of it like an equation, what I'm going to write is I want molarity, which means at the end I want my units to be moles of C6H12O6 on the top and my unit on the bottom to be liters of solution. And I'm just going to set up my calculation and do unit factors so that my final answer has moles on the top and liters on the bottom. So given information, well, we have 2 numbers, 5.00 grams and 100 decimal place milliliters. Well, 5.00 grams I can get to moles. I know it's not in moles, but I'm going to go ahead and write it on the top. And then I know my goal is going to be to turn 5.00 grams of this into moles of that. Now the bottom is supposed to be liters of solution. I don't have liters of solution, but I have 100 decimal milliliters. So my goal on the bottom is going to be to turn this from the unit milliliters into liters. So I'm just going to slowly work my way through this. I'm going to choose one unit and start there. I'm going to start with the grams. Okay, so I'm going to try to convert grams into moles. 180. 0.15588 grams of C6H12O6 in 1 mole of C6H12O6. So my unit on the top is moles of glucose, which is perfect. But right now, the units that are left are moles of glucose on top and milliliters on the bottom, and this needs to be liters. So I'm going to go ahead and set up myself another step where I need to cancel out milliliters and convert it to liters. So you might be wondering, what's that weird 1,000 milliliters to 1 liter thing? How did you magically know that? Remember from chapter 1 when you were supposed to memorize the metric prefixes? Milli is one of those. Okay, the metric prefixes don't die. So if we look at our units, the only units that I have not canceled, moles of C6H12O6 on the top, liters on the bottom. And I wasn't really good at the beginning. I should have specified this was 100 decimal milliliters of solution, so this is still liters of solution. So what I would do here, my units that are left, moles of glucose on top, liters on the bottom, I'm going to grab my calculator and do this all at once. 5.00 divided by 100 divided by 180.15588 times 1,000. And then I would look at my sig figs. This has 3, this has 3, this has a lot. 3, 4, 5, 6, 7, 8. This is an infinite, so 3, 3, 8 are infinity. Which one is the smallest? 3. So my answer is 0.278. And you can either leave the units as moles of C6H12O6 over liters, or you could write capital M. I like this because I only use my calculator once. And for me, that's wonderful. Okay, let's try another one. This time, we're not solving for the molarity. We were given the molarity. I'm going to do this one 2 ways as well. Both the, molarity is an equation thing and kind of the dimensional analysis way. So the definition of molarity, moles of solute, looking at them, I'm going to say Na2SO4, and liters of solution. Now, in general, in this class, unless I tell you otherwise, it's going to be the chemical that I mentioned in the question and water are mixed together. For us, our solvent is almost always water. If it's not water, I will tell you specifically. So let's look at the question and see if we can figure this out. So we're supposed to solve for how many grams of sodium sulfate there are in 15 milliliters of a 0.50 molarity sodium sulfate solution. And the first way we're going to do it is by using the equation up here. So I'm going to try to take the numbers we were given, plug them into the equation, and solve for the thing we're looking for. Well, for capital M, we were given the capital M number, 0.50 molarity. Were we given the liters? Well, almost. We were given 15 milliliters, which I can convert to liters. Okay. And then, check. This, I just fixed it, so check. I can use those 2 numbers and solve for moles. Would that be my answer? Well, it's asking for grams, so I wouldn't be all the way done, but that's what I can do. So let's start there. So capital M, I'm going to write 0.50 capital M. On the top, you can write X because you don't know, or I'm just going to write moles of Na2SO4. That's the thing I don't know. And on the bottom, I'm going to write 0.015 liters. So to get my unknown by itself, I'm going to have to cross multiply. So 0.50 times 0.015 gives me 0.0075. And that's what my calculator says. Now I want to double check sig figs here. 2 sig figs, 2 sig figs, so that is 2 sig figs. So 0.0075 moles of sodium sulfate. Is that my answer? Well, no, because I need grams. So we need to think of a way to convert moles to grams. Well, we were given the molar mass of Na2SO4, and that was not an accident. So we're going to use that. I'm just going to leave that line there. And when I do my math, I will have 2 significant figures for my answer, and what I ended up with is 1.1 grams of sodium sulfate. So in this problem, what I just did, I solved how much sodium sulfite I need to measure out to make 15 milliliters of a 0.50 molarity sodium sulfate solution. This is one of those calculations that people who work in a lab do constantly because this is definitely real life application. Okay, so that was me using the molarity definition like an equation. I'm going to redo this problem with the unit factor method. I miss random things when I do this. This is super fun. But if you're watching this on like 1.5 times speed, that looks amazing. Vroom, 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 vroom. Okay, sorry. I'm done talking about weird things. Let's go to blue. So if we're treating this like the dimensional analysis type of way, we're going to look at the question, look at what we're solving for, look at what we're starting with, and use our unit factors. So what I'm solving for, grams of Na2SO4. Perfect. What am I starting with? Well, the question gave me 2 numbers, 15 milliliters of a 0.50 molarity sodium sulfate solution. And you got to pick only one of them to start with. Okay, well, molarity is technically a unit factor. It's going to be our 4th unit factor that we're going to be adding to our list after chapter 4. So our unit factor, the way I can use molarity as a unit factor, so 0.50 molarity, which means mole per liter, couldn't I say 0.50 moles of Na2SO4 equals 1 liter. We did miles per hour. Didn't we always say if you're going 75 miles per hour, that's 75 miles in 1 hour? Well, molarity means moles per liter, so it's that many moles in 1 liter. So it's a unit factor. That means we cannot start the problem with it because unit factors go in the middle. So molarity, you never start the calculation with the molarity. Okay. We're going to start the calculation with the non-molarity number, which in this case is 15 milliliters. So I'm just going to start doing, canceling stuff out until I get to what I'm going for. Well, 15 milliliters, I cannot use the molarity unit factor yet because that says liters. So I'm going to have to start by using my metric prefix. Then now I can say, well, for every 1 liter, there's 0.50 moles of Na2SO4. Now this unit factor is only true in this question because it was given in this question. Okay. There are other molarities in different questions. That's fine. In this situation, that's the molarity. So if I stopped right now, my answer would be in moles of sodium sulfate. I need to go to grams. So I'm going to have to use the molar mass, which was given in the problem. Cancel out my units, and the unit that's left is grams of sodium sulfate. So it's time to grab my calculator. Take 15 divided by 1,000 times 0.50 times 142.04314. Looks like sig figs, 2 sig figs, infinity sig figs, 2 sig figs, 1, 2, 3, 4, 5, 6, 7, 8. So 2 is my smallest, so I grab my calculator, I get 1.1 grams of sodium sulfate. Same answer. Yep. By the end of this chapter, you're going to have to be able to do this. You have to be able to use a molarity like a unit factor, which is why I strongly suggest this method over the stick it in the definition method. The other problem with using this as a definition is for some reason people forget how to solve for the numerator. They forget how to cross multiply. So they'll take molarity divided by liters to get to moles, which would be molarity times liters is equal to moles. So if you do unit factor, most people end up with the right answer more often than not. So this is same information, was the same solution as the last slide, but what I want you to do is hit pause, try this problem, and then when you're done, hit play, and we'll go through it together. Okay, so I guess this time I will still do it both ways. Molarity is equal to moles of sodium sulfate over liters of solution. So the question asks how many milliliters of 0.50 molarity sodium sulfate are needed to provide 0.038 moles of this salt. Salt just means an ionic compound. So if I plug it in as the equation, I'm going to put 0.50 capital M for the molarity spot. 0.038 moles in the moles spot, and I don't know in the liters spot, so we're solving for liters. So when we rearrange this, it's going to end up looking like 0.038 moles divided by 0.50 molarity. My answer would be in liters. So that is 0.076 liters. Now, is that my answer? It asks for milliliters. So I'd have to multiply by 1,000, and I get 76 milliliters. This might be a mistake, but I'm going to try to do the other way on the bottom. So the question is asking us to solve for milliliters of the solution, and we were given a molarity and a moles. We have to choose one of those two to start with. Molarity is a unit factor. I can rewrite that, 0.50 moles equals 1 liter. So I'm not going to start with that number. I'm going to start with 0.038 moles of Na2SO4. And then I'm going to use my molarity to convert 0.50 moles of Na2SO4 into 1 liter, which is awesome, but I'm not done. I need to get to milliliters, so I'm going to say 1 liter to 1,000 milliliters. I'm going to grab my calculator, 0.038 divided by 0.50 times 1,000, 2 sig figs, 76. This question, the next couple questions actually, are kind of putting together what we've talked about with molarity along with what we did with the ionic and net ionic equations. And just so you know, molar concentration is another way to say molarity. That means the same thing. So the unit molar concentration and the unit molarity are the same thing. So it's asking, what is the molarity of potassium ions in a 0.015 molarity solution of potassium carbonate? So it gave us a compound, but it asked about ions. So that means we need to look at this compound, determine if it's a strong electrolyte, and if it is, look at the relationship between the compound and the specific ion we were given. So potassium carbonate, if we think about our solubility rules, carbonate's in the insoluble section, but potassium is one of those exceptions. So this would break apart, and it would break apart into 2 potassium aqueuses and a carbonate aqueous. Okay, so the carbonate I don't super care about, but what I care about here is the relationship right there. Well, if I have a 0.015 molarity solution of K2CO3, that I don't know what that looks like, but it's what all my threes always look like. You can either kind of eyeball this and say, well, for every one of these, there's 2 of those. Or if you want to write it out, for every one K2CO3, there it is again, there are 2 potassiums. I'd get 0.30 molarity. This gets people. Think about if I have a room full of people who have all of their limbs. And I said, and I have 4 people. How many arms are there? Well, one person has 2 arms, so times 2. Well, that's what's happening here. Potassium carbonate. How many potassiums are there? Well, for every 1 potassium carbonate I have, times 2 is how many potassiums I have. That's all that's happening here. But we do have to combine that with you recognizing that K2CO3, when it dissociates, breaks into 2 potassiums and 1 carbonate. So what it asks, what is the molar concentration of carbonate in this situation? Well, for every 1 K2CO3, there is 1 CO3. So if there's 0.015 K2CO3s, there's 0.015 CO3s. Okay. Let's look at this one, and I want you to practice. I want you to try this. There are 4 scenarios here. In each of these scenarios, 1, 2, 3, and 4, I want you to figure out the molarity of Cl- ions, and then determine which one has the biggest molarity of Cl-. So take a second, figure out what the molarity of Cl- is in each of these 4 scenarios, and decide which one's the biggest. Okay, so for this first one, well, it would break into calcium and 2 chlorides. So the molarity of chloride is going to be, instead of 0.075, it's going to be 0.035. I'm giving stuff away. 0.070. I just take it times 2. 2 to 1. For this one, potassium chloride breaks into 1 potassium, 1 chloride. So the molarity of chloride is 0.040. 100 milliliters of 0.1 molarity potassium chloride, well, that breaks into potassium and chloride. The 100 milliliters, we don't care. We're looking at just the molarity, so 0.10. And then for this one, it's going to break into cadmium and 2 chlorides, so it would be 0.050. Because the 2 chlorides, I had to multiply by 2. So which one is the biggest? Well, I just circled the biggest number. So the 100 milliliters of the 0.1 molar potassium chloride. The 100 milliliters was not important here at all. All you needed to know was the 0.10 molarity potassium chloride. Okay. Last calculation of this video. We have a whole nother video to go still, though, but it's dilution. So the thing I was talking about earlier, when I buy my concentrated cleaning supply and then I take a couple ounces of it and mix it with a gallon of water, shake it up, and then pour it into my spray bottle, and then I use that. That's me doing a dilution. It's taking something that's already been made, but it's too strong, and watering it down, diluting it down, adding water to it to make it weaker. That's a dilution. So in this picture, that's what's happening. This is the concentrated, which are often called stock solutions because they were already in stock. They were already made. And then the one we're getting ready to make is the diluted solution, or it's like your solution, the one that you're making. Okay. So we're taking some of this, in this case, bright blue stuff, and we're transferring very accurately 25 milliliters of it over into this new container. And then from here to here, all I did was added water. just mix it up to the line. Just kind of like when I take my 2 ounces of cleaning supply and mix it with a gallon of water. Well, I pour my 2 ounces in, then I add water until I get to a gallon of water and mix it up. Notice it's the same color. It's just lighter. Well, it's the same chemical, just weaker. That's what a dilution is. A dilution is not a chemical reaction. All I'm doing is adding water. Okay. So when we're doing a dilution, what I want to be able to do here is figure out what the molarity is of this new solution. Like I just made this new wonderful solution. I want to know what its new molarity is. Okay. So whenever we're doing a dilution, the equation that can help us with that, well, for one thing, this is the instructions. Sorry, I'm getting ahead of myself. We use a volumetric pipette as the thing to accurately transfer the liquid from the concentrated to the dilute. And then we use a volumetric flask to fill it to the line so we accurately know the final volume. Okay. The equation for this is M1V1 equals M2V2, where the 1s are the stock or the concentrated solution and the 2s are the dilute solution. M stands for molarity, V stands for volume. At the end of the day, the units don't matter as long as they're consistent from the left-hand side to the right-hand side. So for volume, you can use milliliters as long as both V's are in milliliters. For M's, you only know molarity, so that's our option. Okay, so the 1s I say are the stock, which means it's going to be the bigger molarity because it's more concentrated. And the 2s are the lower molarity and more dilute. The volumes, V1's always going to be small because we're taking a few milliliters of it, and then we're adding a whole lot of water. V2 is going to be bigger. V2 is going to be the big volume because that's where I still had to add the gallon of water to it. So V1, if I'm using my cleaning supply analogy, would be like my 2 ounces. Okay, my V2 would be like my 1 gallon. The issue I would have there is those are different units. I would have to get them to the same units, plop them in, and then I could calculate the concentration of what my new cleaning supply is. So let's practice doing some math with this. Good news is you're going to be given 3 of the 4 numbers. You're just solving for 1 number. We just need to make sure we can practice recognizing when to use this equation and then putting their numbers in the right spots. So how many milliliters of a 5.0 molarity potassium dichromate solution must be diluted, and well, we'll come back to that, to prepare 250 milliliters of a 0.10 molarity solution? Okay, so anytime you see the word diluted, dilution, some form of this word, that's a major hint. M1V1 equals M2V2. Another major hint is when there's only one chemical in the problem, like potassium dichromate is the only chemical, right? It's not a chemical reaction because M1V1, M2V2 is not for chemical reactions. It's when we're always dealing with just one chemical. So we only have one chemical, and in this case I have 2 molarities. So I have 2 of the same thing. Well, M1, M2, or V1, V2. So what can help is maybe make yourself a little table. Once you recognize you're using this equation, let's plug in our numbers. So M1 would be the molarity of the concentrated stock solution. So we were given 2 molarities, 5.0 molarity and 0.10 molarity. M1 is going to be the bigger number. The molarity is going to be bigger. So that means M2 is 0.10. Volume. Well, the question says how many milliliters of 5.0 molarity, so what I don't know is the volume that goes with the 5.0 molarity, must be diluted to prepare 250 milliliters of 0.10 molarity. So the molarity and the volumes are always going to clearly go together. So M1V1, M2V2, 5.0 molarity, I don't know V1. 0.10 molarity, 250 milliliters. I'm going to multiply 0.10 times 250, divided both sides by 5.0. V1 is going to be 5 in my calculator. When I look at sig figs, all 3 numbers have 2 sig figs, so I'm going to add 5.0. And units, well, when I divide both sides by 5.0 molarity, the molarities cancel. The only unit left is milliliters. So 5.0 milliliters. So I would need to grab a 5 milliliter pipette, take 5 milliliters of this solution, put it into a container that holds 250 milliliters, then add water to it till it gets full. Then I just made this solution. Again, this is another one of those calculations scientists, not just chemists, but scientists use constantly. I've used the M1V1, M2V2 equation at home, not just with like cleaning supplies, but I even used it with medication for my babies. So I didn't know with my first kiddo that there's a difference between children's Motrin and infant Motrin, because I was like, infants are children. I don't know. I thought it was the same. So I had infant Motrin and tiny baby. We ran out of it because he had a fever, he wasn't feeling good, whatever. So I went to the store really fast and I grabbed children's Motrin. I bring it home. It's not the same. It talks about like, how many milliliters you need to give instead of kind of like drops for the infant Motrin. The difference between the two isn't the Motrin, it's still Motrin. The difference is that infant Motrin is super strong, super concentrated because they're tiny babies, so you don't want to have to give them very much liquid because they're not good at drinking it. Children's Motrin, you can pour it into those little plastic cups, and when they're 4, they can drink it, and that's fine. So children's Motrin is weaker. It's also kind of a safety thing. Infants aren't likely going to be able to open up the bottle and just chug it because they can't even see their fingers. But children, as they get older, are more likely to just drink stuff that they see familiar, because I don't know how human beings ever survive. I have children, so I'm not being a jerk when I say this, but kids aren't very smart sometimes. So anyway, I got home. I had this baby with a fever, freaking out because first kid. I didn't want to go back to the store. My kid needed to take his medicine. So on the bottle of the infant Motrin, which I still had even though it was empty, it said what its concentration was, what percent. It didn't say molarity, but it said percent. And then it said, what the amount that we had to give the kid, like was it 0.5 milliliters or whatever. And then the children's Motrin, it didn't have, like on the box, it didn't say how much to give a 1-month-old because children's Motrin is for older children and not infants. And so I was like, crap, I can't even give him this. Like, what do I do? So I took the concentration on the children's Motrin and plugged it in right here. I took the concentration on the infant Motrin and I plugged it in right here. I took the amount that I needed to give my kiddo right here of the infant Motrin that I knew from the box, and then I solved for V2, which is how much I needed to give my baby of children's Motrin to give him the same amount of medicine that I would have if it was infant's Motrin. And this equation works for all that. So, I mean, that was a very stressful time in my life. It's scary. First kid, sick kid, you don't know what's going on. But this can be used all kinds of times. So it's not just a chemistry thing. Okay, so what I want you to do, that glorious story that you're like, thanks for that, I really needed to hear that. I want you to practice this calculation. Okay, so take a minute, set it up, do the calculation. When you're done, hit play, and we'll go through it together. Okay, so this is going to be a dilution problem. Not only do I know that because it says so right there, but it says diluted right here. It also only has one chemical, but it gives us 2 different milliliters. So that is our hint of M1V1 equals M2V2. So we read the question. If 10.0 milliliters of a 10.0 molarity stock solution, oh, hold on, that was dumb of me. I don't know. I keep forgetting to fix this typo. Stock solution of sodium hydroxide is diluted to 250 milliliters. What is the concentration of the resulting solution? It shouldn't have said stock there. I'm sorry. So M1V1, M2V2. So M1, well, we're only given 1 molarity, and it's called the stock solution, even though I know that was confusing because I said it twice. The V that goes with it is going to be 10.0 milliliters because it's 10.0 milliliters of 10.0 molarity. So those go together. We do not know the molarity that goes with 250 milliliters. So M1V1 equals M2 I don't know, V2. I'm going to divide both sides by 250. The milliliters are going to cancel, and that cancels completely. So for M2, I get 0.4, is what my calculator says. Now when I look at sig figs, I've got 3 sig figs, I've got 3 sig figs, I've got 2 sig figs. So I'm going to have to say 0.40, and my unit will be molarity. So I just made a 0.40 molarity solution out of a 10.0 molarity solution. You're going to be using this for a long time to come. Like this equation, it just doesn't go away. So in our last video, we're going to look at using molarity as a unit factor in stoichiometry problems. So we're going to combine the mole ratio and molarity together.